For this example, what we're looking at is a drum which is supporting this load at point O. We're going to raise the whole system with these two forces, F acting on the cable on the left, forces 2F on the cable on the right. We know that the drum is originally rotating with an angular speed of omega 1 in the counterclockwise sense. And what we want to know is, after a given period of time, what the angular speed is of the drum and what the speed is of point O. We're looking for a change in speed for change in time. So that tells us right away that the impulse momentum equations are going to be the method that we're going to use. Now, being that the drum and the load move in a different way, their kinematics are not tied together with rigid body equations. Rather, the drum rotates relative to the load. So because of this, what I'm going to do is break the system up into two parts, the drum and the load. And as I draw the forces that are acting on this, it's F on the cable on the left, 2F cable on the right. There is going to be the weight force here of mg, and there will be, in general, an x and y component of force at O due to that load. My x and y, x is going to be to the right, y is going to be up. So when we draw the forces on the load, equal and opposite there of OX and OY like this, we're going to have a weight force there of capital Mg on the load as that. So again, the impulse momentum equations are going to be what we're going to use. What I'm going to do is first look at the drum. There's some forces acting on the drum in Y. I've got F plus 2F minus mg plus OY, like that. So that says that from our linear impulse momentum equation, if I integrate that in time, I'm going to have 3F dt minus integral of mg dt plus the integral of the y component of the reaction force there at O dt is equal to the change in linear momentum for the drum. So this is m VO2 minus VO1. Let me check to see what it says here. Initially, the velocity of O is down, so we'll keep that in. In the end, for VO1, we're going to use a minus 4. But from this, what I'm going to do is actually solve for the impulse due to OY. So this is OY dt is equal to m VO2 minus VO1. I've got integral of 3F dt, which is I'm going to bring on the other side, so that's going to be 3F delta t, because F is a constant force. Likewise, the weight is going to give an mg delta t as that. So this is my first equation, which is coming from the linear impulse equation for the drum. I will also use the angular impulse momentum equation. Summation of moments about O, that's going to be 2F times R, positive, minus F times R, and that's all that we have. So therefore the integral of F times R dt is equal to IO omega 2 minus omega 1. So that's coming from the impulse momentum equation. So since F is a constant, I've got F R delta t is equal to IO omega 2 minus omega 1. So straight away from this equation, we see that the angular speed at time 2 is equal to the initial speed, or the initial speed of omega 1 plus F R over IO delta T. So that gives us one of the two things that we're asked to find. Now for the load. If I sum forces acting in Y on the load, I've got, what do we say, minus OY minus mg, and that's it. So if I integrate that in time, I get minus integral of OY dt minus mg delta t, and that's equal to mass of the load, VO2 minus VO1, as that. So this was my equation 1 up here. I'll call this equation 2. That's one of our answers. So this becomes 3. If I substitute 1 into 3, so that gives me minus MVO2 minus VO1 minus 3F delta T plus mg delta T. And then I have a minus big mg delta T. And that's equal to the change in linear momentum there on the right-hand side for that load. So what I'm going to do is, let's see, group some of my terms together. What can I do here? I'm going to have a 3F delta T remaining there on the left-hand side. I'm going to have a minus M plus M total mass, G delta T. On the left-hand side will remain an M plus big M VO1. On the right-hand side, I'm going to have an M plus M, the total mass again. So it's VO2. So from this, we can see that the speed of the load, speed of point O, at time 2 is going to be equal to 3F delta T minus M plus M delta T plus M plus M VO1 divided by the total mass. And that is our final result there for equation 4. What did we do? Well, when we began, I chose to break the system into 2 parts. And the reason for that, again, is that the drum and the load move in a different way. The kinematics are different. And when you have that, it's good to break things up into 2 parts. So the drum, I wrote down the linear impulse momentum equation, got equation 1. Angular impulse momentum equation for the drum gave me equation 2, which is one of our answers. I went to load, sum forces in Y, and use linear impulse momentum, combine that with the linear impulse momentum equation for the drum, combine those together. No kinematics were required other than to say that O is a common point between the load and the drum, and got this. What we alternately could have done, if you want to think of this in these terms, so alternately, we could have, for part of it at least, for the speed of O, we could have treated the system as a whole. Not for the rotational part, but for the translational part. I think we'll see it's going to give us the same thing. 2F, F, M plus mg. So from that we could sum forces in y, and straight away we get 2F plus F minus M plus mg, like that. So the integration of this, 3F dt minus M plus mg delta t is equal to M plus M of VO2 minus VO1. And I think that you can easily see that these two equations 4 and 5 are the same. So just keep this in mind. If ever in doubt, just break it up into parts. It's a little bit more work, but at least you're sure it's going to be right. But if you can think about it in these terms, if in translation they move the same, put them together. So that would require a different free body diagram for the linear part as compared to the angular part.